Hello, welcome to the next day of the workshop, and our first speaker is Rhea Palak Bakshi, and she will tell us about the structure of skein modules.
Thank you for being here, and thank you to the organizers for giving me the opportunity to give a talk here at this wonderful workshop. So I will talk about skein modules today, and in fact the bulk of my talk will be about the Kaufman bracket skein module. And then I'll talk about some examples. I'll give some properties which will be pertinent to my talk. Then I'll talk about a conjecture about the Kaufman bracket skein module of closed-oriented three-manifolds. And then I'll talk about some recent work about the skein module of the connected sum of two copies of the solid torus. Okay, so there are two names that are synonymous with skein modules. So the first one is and second one is Turaev. So Pshutitsky discovered skein modules in 1987 and Turaev independently in 1988. The difference was that Yosef did this in full generality, whereas Turaev has this very nice paper on the home fly PT skein module and the Kaufman two-variable skein module. So I'll begin with how Yosef defined skein modules. So this is called the N infinity skein module. If you're not able to read at the back, if my handwriting is too small, please let me know. Is this? All right, okay, great. Okay, so some notation first. So S for skein module, N infinity in the subscript. I will always work with an oriented three-manifold. I will have a commutative ring with unity, and this will have some number of variables, B0, B1, Bn-1, B infinity, many variables because it's in full generality, A and T. Okay, and so once again, this is an oriented three-manifold, a commutative ring with unity. These are variables that are in the ring. And how do we define the N infinity skein module? Well, what we do is that we consider formal linear combinations of ambient isotopy classes of unoriented framed links in the oriented three-manifold, and then we mod out, so we mod this whole thing out by three relations. So the first one is the N infinity skein relation, and this is where we use all of our variables. So this is B0 times this diagram plus B1 times this diagram plus B2 times this diagram, and then you keep going on until you have Bn-1 times this diagram, and then you have B infinity times this vertical diagram. So let's understand the skein relation first. So firstly, this skein relation is taking place locally inside of a three-ball in the three-manifold. So inside the three-ball, we have links that appear like this, but on the outside, the links are exactly the same. Okay, so this is the N infinity skein relation. Then the second one is the trivial component relation. So it's, you take the disjoint union of the trivial frame knot with any diagram, you get T times D, where T is a variable in the ring. And then the third one is the framing relation, where you have that this minus A times this. So basically it's telling you that if you were to twist the framing of a link by one positive full twist, it'll be the same as A times the original diagram that you started with. So this is one of the most general forms of a skein module called the n-infinity skein module. And some particular examples of this, when n is 2, you have what Joseph calls linear skein modules, and some examples of these are the Kaufman bracket skein module, which is going to be the skein module that I will talk about in this talk, and even the Q homology skein module. When n is 3, you have the Homefly PT skein module, you have the Dubrovnik skein module, and even the Kaufman 2 variable is an example of a 3-infinity skein module. And then later on, I think in the next talk, Joseph is going to talk about 4-infinity skein modules, which are cubic skein modules. Okay, so let's see how do we get the Kaufman bracket skein module for here. So let's see if I get the substitution right. So if I want the Kaufman bracket skein module, B naught should be -1. Sorry, it should be minus A. B1 should be 1. B infinity should be minus A inverse. Everything else should be 0. See, all the other BI's are 0. E should be minus A square minus A to minus 2. And A should be minus A cube. So what that means is that in the Kaufman bracket skein module, I take formal linear combinations of ambient isotopy classes of unoriented frame links, and then I mod out by 3 relations. The first one is the Kaufman bracket skein relation, and I will write it like this. So I'll just switch around, minus A inverse. Then the second one, when I substitute the trivial component relation, if I take the disjoint union with the trivial frame link, I get minus A square minus A to the minus 2 times D. And the third one is the framing relation that we have. Okay. So this is the Kaufman bracket skein module of unoriented 3 manifold. We work over ambient isotopy classes of unoriented frame links. All right. So these are the most extensively studied skein modules of all in all literature, and they have many interesting connections to many fields of mathematics. So I'll just write a few of them here. So for example, the skein module, the Kaufman bracket skein module, is related to the SL2C character variety of the fundamental group of the oriented 3 manifold. This is work by Bullock, Shatitsky, and Shikora from 1997. They are related to quantum Teichmuller spaces. Quantum Teichmuller spaces. This is work by Bonahon, Wang, and Lei. You can categorify Kaufman bracket skein modules. So this was by Marta Saida, Shatitsky, and Shikora again. And then for RP3, this was done by Gabravshik, Boston Gabravshik. And I'm running out of space, but let me, here. I would like to mention that they make an appearance in the AJ conjecture. So this is a conjecture that relates the A polynomial of a knot with the colored Jones polynomial of a knot. And they also related to quantum cluster algebras. And this is by work of Greg. So there is a lot of rich theory and rich structure here. And okay, so first part is done. This is a Kaufman bracket scale module. And on to some examples that are interesting for us in this talk.
Can I ask a
Yes.
question? How do I see that monthly PT scaling module in special case?
So you will work with so you will have three horizontal diagrams, and then you have to make an appropriate substitution of B0, B1, B2. If you work with the framed version, then you will have a variable B infinity, otherwise this will be 0. Yeah.
And we can still work with unoriented.
Yes. So you can work with oriented. So this is not fixed. So you can work with oriented frame links. You can work with unoriented frame links. Only oriented frame links, in which case you won't have a framing relation. All of that is possible. So for example, the home flat PT scale module works only over oriented links. The Kaufman 2 variable is over oriented frame links or unoriented frame links, depending on how you define it. But all you need to do is make a substitution for the variables and work with the appropriate diagrams. That's all. Yeah, so the home flat PT scale module is an S3, so it's a 3 scale module, so there's no infinity. The Kaufman 2 variable is a 3 infinity scale module, and so on. Any other questions? Okay, and the cubic scale modules, I think Yosef will speak about in the next talk. All right, so some examples of the Kaufman bracket scale module. So the existence of the Kaufman bracket polynomial is, of course, due to Kaufman. So for S3, we know that this is simply isomorphic to, if my ring is the ring of Laurent polynomials with integer coefficients times the empty link. So this is free with one generator. Then you have Jim Hoste and Pshititsky, who in 1989 computed the Kaufman bracket scale module for length spaces over the ring of Laurent polynomials and integer coefficients. So they showed that the scale module, so this is S2 comma infinity, that's notation for the Kaufman bracket scale module, of a length space PQ where P is greater than 0. This is free over the ring of Laurent polynomials, and it has the floor of P by 2 plus 1 free generators. And then when P is 0, so that means that when we have the scale module of S1 times S2, Jim and Yosef did this the following year, and they showed that this has this nice decomposition into free and torsion modules. So this is 1 minus a to the 2i plus 4, if I remember correctly. So Jim and Yosef showed that the scale module of S1 times S2 has this decomposition into free part and torsion part, and this is an infinitely generated torsion part. And this is going to be important because this will make an appearance in Marchais' conjecture. And the other thing that I want to mention is that the reason why we have torsion in the scale module is due to the presence of the non-separating two-sphere. So when you have a non-separating two-sphere in a 3-manifold, you can do the Dirac trick, which will give you a torsion element. Okay, some other interesting examples. So this is again by Jim and Yosef. This is in the following year in 1991, where they computed the skein module of the Whitehead manifold, and they showed that the skein module is infinitely generated, torsion free and not free. And this is in stark contrast with the skein module of R3, which is generated by one basis element. And then for a closed surface, a closed oriented surface times S1, now over the field of rational functions, a couple of people did this. So for the 3 torus, this was computed by Carrega. And so Carrega showed that there are 9 generators, and then Gilmer came along and showed that they are linearly independent, forming a basis. And then when the genus is greater than or equal to 2, so this case was done by Cherry and Wolf. And what all of them showed is that it's a free module over the field of rational functions, and the dimension is 2 raised to 2g plus 1 plus 2g minus 1, where g is the genus of the surface. And then lastly, this is a result by Chititsky from 1987 again. And he worked with the skein module of any oriented surface times the interval. Of course, you can work with any ring, but let's just work over the ring of Laurent polynomials for now. He showed that this is free, infinitely generated, and it's infinitely generated by the empty link and links in the surface that have no trivial components and no crossings. Okay, so one example of this is, say if I want to work over the thickened pair of bands, then Yosef's theorem will tell us that if this is my pair of bands, this is A3, A1, A2, so these are the boundary parallel curves. Then Yosef's theorem tells us that the skein module of the pair of bands is generated by monomials in this form, A1 to I, A2 to J, A3 to K, where I, J, K are greater than or equal to 0. And when I, J, K are exactly 0, we have the empty link. Okay, so this is the skein module of the pair of bands. And in fact, because the thickened pair of bands is the genus 2-handle body, we also get that the coffin bracket skein module of the genus 2-handle body is generated by monomials of this form. Okay. Any questions so far? Okay, so this brings us to one digression. This is an important class of manifolds for skein modules, because you can enrich the coffin bracket skein module of a thickened surface with an algebra structure where multiplication is given by stacking, so placing one skein over another skein. And the reason why this is important is because the coffin bracket skein algebra of a thickened surface is isomorphic to the coordinate ring of the SL2C character variety of the fundamental group of the surface. So this is where we get the connection to algebraic geometry from the skein module of a thickened surface. All right, so now we can discuss some properties which will be pertinent for our main result. So most of this is again due to Yosef from the same year, so 87. And the first one says that if you have an orientation preserving embedding between two oriented three manifolds, then what you have is a homomorphism between the corresponding Kaufman bracket skein modules. The second one involves three manifold topologies. So the first one is that if you have an oriented three manifold that's obtained by gluing a three handle to the original manifold M, then we have an embedding from M3 into M3, and in this case you have an isomorphism between the Kaufman bracket skein modules. So three-handle addition doesn't change in a way the Kaufman bracket skein module. The third result is, maybe I'll write that on the next board, or maybe I'll write that here. This involves two-handle addition. So say we have some manifold with boundary, and on the boundary you have some simple closed curve gamma to the angular neighborhood of which you glue a two-handle, and say this resultant manifold is M3, then the associated embedding gives rise to an epimorphism of the corresponding Kaufman bracket skein modules. And the kernel of this epimorphism is generated by handle sliding relations. So the idea is that you could have inequivalent links in the original manifold, but once you glue a two-handle, you could slide one link across the two-handle, and in the resultant manifold, those two links could be equivalent. So what happens is that the kernel of this epimorphism will be generated by all such handle sliding relations. So there will be relations of this form. So if L is a generating element, so it's a generating element in the skein module of the original three manifold, and SL gamma is the result of sliding that link across the two handle, then L minus SL gamma will be one of the generators of the submodule of handle sliding relations. And in fact, this is important because what computing Kaufman bracket skein modules essentially boils down to computing this submodule of handle sliding relations. So this is the trickiest part whenever you have to compute the skein module of an oriented three manifold. So another thing, what both of these results tell us is the following, that any compact oriented three manifold can be obtained from a handle body by gluing three handles and two handles. So three handles only give you an isomorphism. Two handles give you an epimorphism. You're creating relations. So you essentially need two things. Because you can obtain any compact oriented three manifold from a handle body, you need the skein module of a handle body, which is given by Yosta's result. And then you need these handle sliding relations. And we know how to compute the skein module of a handle body, as I mentioned here. Okay? You may wonder what one handle addition does. Well, you will get more generators because you'll have more possibilities for curves there, and for zero handle addition, you would just get a tensor product of the corresponding skein modules. Okay, and the last property that I want to discuss is a very important property. So this should be number 4, I guess. So this is Witten's conjecture, which is now a theorem, due to Cunningham, Jordan, and Safronov. I think their paper came out in 2019 and it was published just last year. And the theorem says that the skein module of a closed, so this is closed, oriented 3 manifold over the field of rational functions is finite dimensional. So over the field of rational functions, our skein module is finite dimensional. This is not true over the ring of Laurent polynomials. As I mentioned before, the skein module of S1 times S2 is infinitely generated. So this is not true over the ring of Laurent polynomials with integer coefficients. As I mentioned, S1 times S2 is infinitely generated. And so the question arises really that what is the structure of the coffin bracket skein module over the ring of Laurent polynomials? So the point is that you know much more about the structure over the field of rational functions than over the ring of Laurent polynomials. So to this end, Julien Marché conjectured sometime in 2018 or 2019, I believe. So he said that the coffin bracket skein module of closed, so again our oriented 3 manifold in this case is closed, but over the ring of Laurent polynomials with integer coefficients, has a decomposition into free modules and torsion modules. NK are torsion modules and they're torsion modules of a particular kind. So these NK are a to the k minus a to the minus k torsion modules for each k greater than equal to 1. And if you remember the structure of the skein module of S1 times S2, you saw that it satisfied this structure. So for S1 times S2, D is 1, and then this was A to 4i minus A to minus 4i, or some such thing. This is also true for the product of a closed oriented surface times S1. Renaud and Wolf had showed that their proof over the ring of Laurent polynomials shows that the skein module for the product of a surface times S1 has this decomposition into free and torsion part. But what happens is that in general, this is not true. So I observed that RP3, connected sum RP3, is a counterexample. I'd like to give you a little idea about what the structure of the skein module looks like. So the skein module, the Kaufman bracket skein module of RP3, connected sum RP3, has two copies of the free part, and then I should write it differently. So it has two copies of this free part, and then it has this rather messy part which is not cyclic. And so this is a submodule of this extended ring of the ring of Laurent polynomials, and it's generated by two relations, and I'll write down one of the relations. So it's generated by a to the n plus 1 plus a to the minus n plus 1 times Sn of t minus 1 minus 2 times a plus a inverse times this sum of a raised to n plus 2 minus 4k when n is even. So the reason why I wrote this down is to show you that firstly, the submodule, so this part is not cyclic. Secondly, this relation involves this term, Sn of t. And what is Sn of t? So Sn is the Chebyshev polynomial of the second kind. And Chebyshev polynomials of the second kind, they're very dense in skein modules. They make an appearance everywhere. How are they defined? They have this recurrence relation. Sn plus 1 of x is x times Sn of x minus Sn minus 1 of x, with the initial conditions that S0 is 1 and S1 is x. And they're going to make an appearance in the main result as well. So two things, this is not the cyclic part, this is not a torsion part. And secondly, in one of the relations that generates this submodule over here, Chebyshev polynomials of the second kind make an appearance. So the big takeaway, I should mention that Machkovsky and his work on arrow diagrams is why we have this structure for the skein module of RP3 connected sum RP3. So the big takeaway is that while for all the examples I had listed before, Marchais' conjecture holds, but the moment we talk about connected sums of three manifolds, you have a counterexample to this, to the splitting into free and torsion part. So in a bit to understand what the structure of the skein module would be, over the ring of Laurent polynomials, I decided to study the skein module of the connected sum of two solid tori. So this brings me to the main result. Okay, so we did examples, we did properties, we did Marchais' conjecture, and now the skein module of H1 connected sum H1. So H1 is the genus one handle body. This is also the solid torus. And so here is a result. Oops. This is joint with Tangley and Yosef Pshititsky. Okay, so the idea is as follows. So H1 connected sum H1. How do we get this connected sum? Well, what we do is that we start with the genus two handle body. We take the disk that separates these two toroidal holes, and then I take the boundary of the disk, which is going to be my curve gamma. And then to the annular neighborhood of the boundary of this disk, I glue a two handle. So this is H2, which is also the thickening of the pair of bands. And so if I take a curve, this curve over here, and to the annular neighborhood I glue a two handle, I get H1 connected sum H1. So Yosef's handle sliding lemma tells us that the skein module of H1 connected sum H1 should be exactly the skein module of H2, but I've glued it to handle, so I will have handle sliding relations. And then what are the handle sliding relations? They're exactly of one kind. So our result is that J is generated by handle sliding relations of this form. So what are ZK and what are UZK? So say I have K strands that intersect the curve gamma along which I glue my two handle. Then I can slide the top arc across the two handle to get, so let me draw this like this. This diagram. And then you can use the Radameister 1 move, both cases, and then what you get is a raised to 6. And this is our diagram, UZK. So our result says that just handle sliding on the top arc is enough. And the second result is as follows. So I'd like to give one example of how we get our second mean result. So say k is even, so say k is 2. Okay, so what we have is that we have our, so I'll just draw it on the pair of bands. So we have this curve, which is the boundary curve A3, all right? And then handle sliding tells us that this has to be equivalent to a raised to 6 times so like this, to this curve, all right? And then you can use the Coffin bracket skein relation, and what you will get is that this is equivalent to a raised to 4 minus a raised to minus 4 times a3 plus a square minus a raised to minus 2 times a1, a2. And I can rewrite this as minus 1 square curly to s1 of a3 plus curly 1 of s1 of a1 times s1 of a2, where my si's were the Chebyshev polynomials of the second kind that I had defined. So when you do k equals 3, 4, 5, 6, you will get something that involves Chebyshev polynomials of the second kind, and our result, which is in progress, I'll write in progress here, is showing that the Coffin bracket skein module of the connected sum of two solid tori, the handle sliding, the submodule of handle sliding relations is exactly generated by this relation. So minus 1 raised to n plus 1 curly n plus 1 times Sn of a3 plus curly braces of 1 times Sn of a1 times Sn of a2, where n is greater than or equal to 1. And over here, curly braces means a raised to 2k minus a raised to minus 2k. And so you can see that the handle sliding relations in this case also involve Chebyshev polynomials of the second kind. Are there any questions so far?
You should say that your k is equal to n in the formula.
Oh yeah, k equals to n in the formula, yes. Yes, yeah, k equals to n. So over here, n is 1. So it's intersecting this curve twice. Okay, so I'd like to give an idea of the proof of a mean result. Okay, so we appeal to relative Coffin bracket skein modules for our mean result. So what we do is that, say we have this angular neighborhood of our curve gamma. On gamma, what we do is that we place two marked points, say let's call them U and V, which divide this curve gamma into two curves. So this is gamma 1, sorry, I'll call this gamma 2, and this is gamma 1. And so now we are working in the relative case, so that means that we have relative curves, which are curves that connect the mark points with each other. We're still in the Kaufman bracket setting, so again we resolve by the Kaufman bracket skein relation and trivial component relation. But the idea is as follows. So now, I'll just draw this part. This is my curve that has 2 mark points. If I fix tangents on these points so that any relative curve alpha always approaches u and v from the left, then what is handle sliding doing? Handle sliding is simply replacing this curve, which is alpha union gamma 2, with the curve alpha union gamma 1. So if I were to introduce some homomorphism from the relative Kaufman bracket skein module of the genus to handle body to the absolute Kaufman bracket skein module of the genus to handle body, which maps any relative curve alpha to alpha union gamma 1 minus alpha union gamma 2, then the image of this homomorphism gives me the handle sliding relations of the Kaufman bracket skein module of the genus to handle body with the 2 handle attached to it. So the image generates all the handle sliding relations. And just to recall, as I mentioned before, computing this set of handle sliding relations is always the most important thing that you do when you want to compute the skein module of a 3-manifold. And so I would just like to write down the steps of what we did. So we have a proposition that the generators of the relative Kaufman bracket skein module of the genus to handle body are of the form C0, A3 to I, C1, A3 to I, C2, A3 to I, and CL option, right? CL, A3 to I, and CR, A3 to I. Where what are C0, C1, CL, CR? They are these diagrams. So we have 2 mark points, 2 mark points, 2 mark points, and 2 mark points. And so this is the relative curve C0. This is the relative curve C0. This should be the relative curve CR. And I just realized that I misdrew my CL. But you have another CL, which I don't remember how we draw. But Joseph, do you remember how we drew CL? I think it should be... But I don't want to lie, so I will let this be and then I will look it up.
The one did it, but if you twist first, so that's...
Yeah, so, but there is another curve. All right, and so what our result says is that you just have to look at the image of all these four curves. And what we got was the following. So we got that the image of CL is exactly the sliding, so I have ZK. I get a raised to minus 6 of this sliding, which is sliding on the top arc, but just in the other way. And we got that the image of CR is what we call ring sliding. That means that if you have a ring that surrounds these arcs that intersect the curve gamma, then you can slide this across the 2 handle to simply get it unlinked. The image of C1 was 0, and the image of C naught is, this follows also from ring sliding. And then the last thing that we had to show, of course, was that ring sliding follows from this sliding, and this proves our main result. Okay, so just to reiterate that we used relative coffin bracket skein modules to describe all of our handle sliding relations. Now, why is the skein module of H1 connected sum H1 important? The reason is that these relations will sit in the coffin bracket skein module of the connected sum of any other closed oriented three-manifold. So I'd like to finish with some future directions and some very recent work that I did. So this was joined with Seongjong Kim and Xiao Wang, where we computed the coffin bracket skein module of S1 times S2, connected sum S1 times S2. And I would just like to mention two things. The handle slidings involve Chebyshev polynomials of the second kind. And in fact, this skein module also doesn't have a decomposition into free and torsion modules, so we have another counterexample to Marchais' conjecture. And in fact, what we do conjecture is the following, that that the skein module of any closed oriented three-manifold over the ring of Laurent polynomials, so the connected sums of two closed oriented three-manifolds over the ring of Laurent polynomials, does not have this decomposition into free part and torsion part. And so some odds and ends. Keeping our goal of trying to understand what the structure of the skein module is over the ring of Laurent polynomials, some immediate results that people could possibly work on is to compute the skein module of the k-connect sum of H1, the k-connect sum of S1 times S2. What is the skein module of the connected sum of handle bodies of arbitrary genus? So there was a theorem about this that was published by Yosef, but then we later found out that that result was not true. So the result is actually that the skein module of this connected sum is not generated by only the handle sliding for H1, connected sum H1. So you need more sliding. So handle sliding on the top arc is not enough. So we don't know what handle sliding relations generate the coffin bracket skein module of Hn, connected sum Hn. You can generalize this to arbitrary connected sums of length spaces as well. And we did spend a lot of time talking about connected sums of three manifolds, but what about just prime three manifolds? So here's a conjecture I'd like to leave you with, that the skein module of an oriented prime three manifold, so prime closed oriented over the ring of Laurent polynomials has a decomposition into free and torsion parts. So we conjecture that For prime, you have that decomposition that Marche had conjectured, but for connected sums, it definitely does not, but we don't know what the structure would be. So, thank you so much.
Questions?
Yes.
So you said that this Witten's conjecture is true, that over the ring of rational functions the dimension is finite. So
Yes.
is it predictable?
It is not constructive, the proof. So you don't know what the dimension would be, but you just know that it's going to be finite dimensional. Yes. So then you have to appeal to algebraic geometry. That's some new results by Cherry, Adam, and Effie, where they tried to do some Dane fillings of manifolds and then computed the skein module to show. But it's not constructive, so you don't know what the dimension would be.
Other questions?
So when you define the skein module, there are a bunch of parameters, B0, B1, etc.
Yeah.
Are there any similar results for different parameters?
So Joseph would probably talk about cubic skein modules. So when you have 3 horizontal diagrams and 1, but more the variables, meaning bigger the skein relation, more the complexity. And I hope Joseph will touch upon that in his talk. Yeah, but it is not easy. I think the easiest ones are the linear one, the Kaufman bracket that I discussed, and then the Homefly PT Kaufman two variable.
And cubic in between, impossible and possible.
Yeah.
I have questions as well. But maybe that-
Yeah.
Can you go back to surface cross S1? You said that here there's concrete answer for the Witten conjecture, yeah?
Yeah, so for this manifold, so this is closed, so this is a closed surface and it's oriented. So Carrega, Gilmore, Cherry, and Wolf showed that the skein module is finite dimensional and it's 2 raised to 2g plus 1 plus 2g minus 1, where g is the genus of the surface.
But really they said something about torsion, because you said that this...
So this was done over the field of rational functions, but Cherry and Wolf showed that for their case, and they computed when the genus is greater than or equal to 2, their proof shows that over the ring of Laurent polynomials, they have this decomposition into free and torsion. But just, yeah, so you can get that from the proof.
Not exact structure, but the composition.
Yes. I think they actually did give what NK would be for, so what the torsion modules would be for this case. They,
It is some of cyclic, but
Yes.
I cannot believe that they did general, because every torus in this product is new set of torsion.
They did, in
Yeah, I
fact.
should do that better,
Yeah.
yeah.
I can share the paper with you after this.
Any other questions? If not, let's thank Rhea again. Don't worry.
I can use this in my talk.
Very good. Yeah, so let me stop the recording.